Welcome at the Innovation Café. Nice to see you online with us. I hope you all enjoyed the talk by Erik today. We're going to do a little Q&A. If you have some questions, you can put them either in the chat or you can raise your hand and ask to be unmuted so I can unmute you and you can ask your question yourself. Up to you. Otherwise, I'm going to read them out loud via the chat. Erik is going to answer some questions for us. So Erik, thanks for joining us. We really enjoyed your talk today. It was nice and in-depth, but I think a very clear story. And I have a couple of questions for you, so I'm very curious to hear about it. Obviously, your story was already quite clear, but what I missed a little bit was your own background. You didn't really say anything about how you ended up in this field of work. So I was wondering if you could share a little bit about that.
Nice question. I studied chemistry in Utrecht. I also did my PhD there. And after that, I went to Philips Research. So in Eindhoven, that's how I ended up in Eindhoven. I've been working at Philips for 9 years. And when I was at Philips, I started to work on nanowires, actually for different applications. So one was for integrating these 3-5 materials in silicon technology for high-speed transistors. And I ended up with working on gas sensors, also with nanowires. And then in 2010, I decided, okay, let's go for an academic career. So I applied at the Eindhoven University and in Delft. So then, since then, I had a dual position, so in Delft and Eindhoven. And since, 3-4 years, I'm in Eindhoven. And well, we are still working on nanowires.
Yeah, that's kind of nice that you always kind of have been in the same field, but in different types of applications, right? Going from like really practical to like almost academic in that way.
Yeah.
Yeah, nice. So next question was going to be, how long have you been working on this because I mean, this research has been taking for a while, I'm assuming. You started this research completely when you started at the TUE, or was it already, did you come into this project halfway, or how does that work?
Yeah, so that's interesting. So when I started at the university, so I had to write proposals, so scientific proposals to get funding. And I think I started to write, so in 2010 I went to the university. So I think in my first proposal, I proposed this work. So that was 2010 or 11 or so.
Oh wow! Okay,
that's how long it takes before.
And so did you? I mean, I have no idea how these processes go. So sorry if this is a really ignorant question, but how long does it take for something like that to be granted? Like, is it straight away the next year, or did it take a couple of years before you could actually start the research?
Well, normally that takes between half a year and a year, so then you can start. But then you have to hire students, so PhD students. And before they are up and running, it takes a year, I think, before they have had all the trainings and before they really know how things are working in the lab.
Yes.
So then, that gives a delay already of 2-3 years.
Yeah, exactly. But because you're mentioning you're working with PhD students, which I think is fairly regular at your job, right? But don't they, because normally a PhD is around like 4 years or something, right? And the research has basically been going for what, like 8 years? Does that mean you had to switch your team?
Yeah, so this is actually, so the students which were on the slide are the second generations of students working on this. So first people started actually to optimize these core wires. So if you remember, so we have this core shell structure. Yeah. And we first focused on getting a high quality core wire. Okay. And that took really 4 years.
Wow, that's intense.
Yeah.
I mean, when you talk about it like this, it seems so simple, right? But I know it's not. Yeah. It's just like nice to see like that there's so much progress included in it. And you mentioned that it was included into a European project as well. Is it a bigger, also focusing all on like photoelectronics, or is it just like part of a completely different thing? Can you tell a little bit more about the bigger scale of the project?
Yeah, so that European project is really focusing on getting lasing from silicon, so from this material system. So that project started about 4 years ago. So that will end coming January. And yesterday, actually, we heard that the Followup project is also granted. So
Oh,
we can continue with this work.
so that's, and the Followup project are also being included in that?
Yeah.
Okay. Oh, or you mean your Followup project, you mean?
Okay, so during the Corona period, so we wrote another European project. And that has been granted now, and that's actually just a follow-up of this work.
Ah, okay.
That's really continuation.
Okay, fair enough. Let me check. You mentioned that it's basically already been known for about 50 years that, I'm sorry if I'm saying this wrong, but like this mix of like silicon and geranium is a good for emitting light, right?
Yeah, so it's not the mixture, but it's the crystal structure. So if you make it hexagonal.
Sorry, yeah, exactly. But people already know that for 50 years, right? That's what.
Yeah, so there's a paper from 1972 where they have published these predictions, these calculations.
Yeah, but I mean, like you said, it's taken a long time before it's actually happened that this was possible to accomplish. Can you say like what did you do differently? Like how come now it is possible? Is that based on a different approach? Is it based on technology? Like, can you elaborate a little bit on that?
Yeah, well, very good question. So people have tried this with strain. So if you have a crystal and you strain it, so you compress it or you pool, so then in principle you can form very small volumes of this hexagonal material. But that was always heavily defected. So I think you can imagine that if you have a crystal and you pull or you squeeze it, that you can get defects, and that was the case. So people could never really study the optical properties. And I think what made this possible is the development of the core wire. So the gallium phosphide or the gallium arsenide, let's say. So the optimization of the crystal structure of that core wire, which could be copied then to the silicon germanium. I think that was a technology that actually enabled this work.
Yeah, and is it also due to the development of technologies that that's now possible? Like, are there other technologies now available that weren't available then? Or that's not really the case?
Well, yeah, so what also happened is that the Netherlands started to invest a lot of money in nanotechnology since, since when was it? Well, beginning of 2000, I think. So that's called NanoNet. And for instance, so we need lithography, e-beam lithography, to make very small structures. And these wires are grown out of a very small catalyst particle, which has to be defined by this lithography technique. And that was simply not available before that time.
Yeah.
So let's say, so we have the development of nanotechnology, and we have, let's say, the development of these nanowires with different crystal structures. And these came together, and that opened these new areas.
Okay, great. Well, that's good to hear. Let me check. You mentioned you have the Indian phosphide and the silicon combo. That's also basically doing the same thing, right? Is that is it just the fact that it's expensive? And I mean, you're also saying that it doesn't integrate as well on a small scale. But is this being used in other applications right now? Like that, that is, how do you say that? Not so much on a smaller scale, for example, but on other levels?
Yeah, so this is now, I think, the mainstream technology in integrating photonics into silicon technology. Yeah, so people are using this at this moment mainly, I think, for information technology. But for instance, today I heard a talk about sensors. So you can also use light and light detection for chemical sensing.
Okay. Let me check.
Good questions.
I've done my homework. Let me check. I'm not sure if I just missed this part in the presentation, but you were mentioning that germanium in itself is like a good light emitter. Is that correct?
No, so not the cubic germanium, but if you make it hexagonal,
yeah,
then it is good light emitter. Yeah.
But like, why do you have to I mean, obviously you work with silicon, but like, why is the connection with silicon so important then?
Well, because silicon is the mainstream technology.
Okay.
So in this technology, you always start with a substrate, so with a wafer.
Mm-hmm.
So that is a big well, plate made of silicon, and that's a single crystal. And well, silicon is affordable.
Okay.
I mean, these wafers also exist from germanium, but these are super expensive because also germanium is quite a rare element.
Okay, well that answers my question. That's good. Then you mentioned the next steps. There is obviously for you guys in this whole silicon technology, there's a lot of new developments, but you were also mentioning Li-Fi and gas detection. And these are things I guess are more, maybe not all relevant for us as like the general people, but Li-Fi I can imagine is very interesting for us because it can open up new possibilities. Do you have any idea on like how soon, for example, because now you had this breakthrough, do you have any idea like how long it will take before these types of things can be developed?
Yeah, it will take a long time. It's my experience.
Yeah,
so that's good.
It's already too like
being in industry. So from let's say science to product, that takes very long. I mean, well, you have to first of all. So now we are really at the lowest what's called the TRL level, so technology readiness level. So this is just basic science. And to go from, let's say, this fundamental science towards a device, and then in the end it has to be produced. Well, it may take 10 years, for instance.
Okay. Well, that's actually not too bad yet. Then I mean, considering the research already took 10 years and like the application towards new things, and I can imagine like these technologies are also continuing to grow and grow and grow, and like then 10 years to having it included into something like that is actually, in my opinion, not that bad.
Okay, sounds long, isn't it?
I mean, for me, it's amazing that these things are already possible anyway. So I'm not too fuzzy with that. Let me see. I have one more question, but I think we already. Yeah, I read, so there was an article on the TOE, which is also how I found you. And they were saying like, this is the holy grail of photoelectronics. Is it really considered to be like that? It's really considered to be like the highest thing achievable? Are there other goals in this type of field that are other developments that are really considered to be like something essential for this type of field?
Yeah, that's a very good question. So, so the silicon roadmap started like in the 60s somewhere. And it was already in the beginning that they realized, like, actually, if we could use light for optical communication, that would be well, very good. Well, for information transfer. But then they also realized, like, it will be very difficult with silicon to create light emission on a chip. So people have been trying to combine these other semiconductors with silicon, and so far it has never been really successful. But a lot of well, universities, but also industries, they have really attempted to integrate photonics into electronics. So now this roadmap is kind of so this roadmap of scaling electronic devices has two drivers. So one is economics. So if you simply make transistors smaller, then you can put more on a chip, so that will make them cheaper. But secondly, it's also the performance. So if you make the devices smaller, then the performance is increased. But this performance increase is not happening anymore since 2005 or so because of this resistance. And so this roadmap is kind of stopping. So we are a bit at a cross point.
Yeah.
And an alternative technology could be something like quantum computation.
Sorry,
so
you have to explain
computation. So that's a completely different way of making electronics.
Okay. you were mentioning like funding and everything. I can imagine there's also a lot of companies that are interested in the research that you're doing. Are you also working closely with companies in developing these things, or is it really just the research and these types of company collaborations come in later?
Yeah, so so in this project also IBM is involved. It's IBM Research in Zurich. What I like about them is that they really have an academic attitude, so they like to do fundamental science, while they also keep an eye on the application. So for me, that is perfect. Well, we have been approached by some companies, but at this moment, I think it's too soon.
Yeah, I can imagine.
And to my experience, so if a company would step in and would give funding, then also they really put you under pressure.
I can also imagine, so as a researcher, you don't really want to be dependent on a company, and specifically also because then they want to push you in a certain area which you might not want to go into.
Yeah, exactly. So for the moment, I think it's fine. And maybe if we have lasing, if we start to make serious devices, then I think it's nice maybe to hand it over to a company.
Yeah.
But I think it's too early now.
Yeah. And for now, you're just going to continue on with the development of the project and go for another 10 years maybe.
Yeah.
Well, those were my questions. I don't think we have any other questions from our audience. I don't know if you want to have anything else to share with us, but otherwise, then I really want to thank you for answering my questions. I hope they weren't too dumbed down.
Sure.
And thanks everyone for watching. I hope you still enjoyed, even though you didn't have any questions. And Erik, once again, thanks for everything, and have a nice evening.